one strip and one eye patch per person.
Okay.
Hello? Just in the last few minutes before we get started, I want to make sure everybody has a strip and an eye patch. If you don't have a little strip of paper and an eye patch, make sure you come down and grab one. Thank you.
What did I tell you?
They can grab it as well. It doesn't matter.
Fine. We keep track of just showing.
Well, the Static Physics Series, my name is Paul Beal, one of the organizers. Before we start with the introduction for today, there's a talk on December 7th by Professor Marcus Rashkin, and he's going to talk about rare earths, physics, and international politics of rare earths. And the next one after that in the spring semester will be January 25th, and the speaker entitled "To Be Decided." We're in the process of organizing the meeting. Well, let me introduce today's speaker, Professor Bethany Wilcox. She's from Colorado. She got her undergraduate degree in astrophysics here at CU. She got her PhD in physics here at CU. She was on the faculty at the Colorado School of Mines for a few years until she joined the faculty here in 2018. Her physics education research program is very well recognized and well funded, and she has a focus both on studying, teaching, and learning both in ordinary courses and also in teaching laboratories. One of the leaders of that. Bethany was recognized this year with the Boulder Faculty Assembly Excellence in Teaching and Pedagogy Award. And ladies and gentlemen, please welcome Bethany Wilcox.
Awesome. Thanks, everybody. Super excited to be here and get to chat with you all. This is the first time I've ever given one of these Saturday physics lectures. This may be a little bit unusual for a Saturday physics lecture, and certainly we're going to flirt a little bit with the barriers between physics and biology, but that can be a bit of an artificial barrier anyway, so we'll make do. So the title of this talk is The Physics of Vision and Perception. I want to sort of just mention the first thing, if we're gonna start thinking about how we perceive the world, what things impact that? What decides how we perceive the world? Well, there's three important elements to this. The first is light. Light is what our eyes detect. Light is the main way that we interrogate the world. That's actually true even at the highest scientific levels. The vast majority of what we know about the world we've learned somehow through interrogating light in some way. Then the next is the obvious one. Our eyes. Our eyes are the next part of that, the interaction between light and our eyes. And the last one is the one that most people forget, but it's actually, I might argue, one of the most important parts of this, and that is the brain. All of these things work together to influence how we perceive the world around us. We'll talk about all three of these today, but I'm going to start with light. So to make sense of light, I want to think about how light behaves, how it interacts with things around it. Physicists often model light in one of three ways. The first, and actually the original way that way back when we ever thought about light, was light as a ray. And so that's kind of like what you think about when you think about a laser pointer. It's kind of a stream, a continuous stream of light. It goes in straight lines until it hits something. Maybe it bounces off of something like a mirror. Maybe it gets absorbed. Maybe it scatters in some way, but it kind of just moves in straight lines, and that's kind of it. For a long time, that's exactly how we understood light, and that's all that we thought light was. And then we started observing interesting things that couldn't be explained with this model of light. We started seeing light do things that didn't make sense. And we realized that actually to explain these different phenomena, we had to think of light in a different way. And we actually had to think of light as having wave properties. And when I say wave properties, you can, on a surface level, very much think of these waves on an ocean. So it has amplitude, it has wavelength, how long does it go to be able to repeat itself? It has energy, it actually moves energy through the medium. And we were able to explain a lot of the odd things that we saw by thinking about light as a wave. And then that model failed, and we started seeing interesting things that we couldn't explain using light as a wave, and we realized sometimes in weird situations, light actually behaves as a particle. And it maintains its wave nature, so we actually think of these particles as little wave packets. Now, if you go on into physics, a lot of the physics you'll talk about will focus on that last model of light as a wave packet. It's actually the least relevant for us today. So the vast majority of what we need to understand vision is really just these first two models. And mostly it's the first one. So we can actually go back to mostly thinking about light as just a ray, kind of our old-timey original understanding of light. But we do have to pay attention a little bit to some of the wave properties, and we'll see that happen. So let's map out this process. We have an object, in this case, the sun, and we have a person here waiting to observe it. The sun gives off light. I've drawn it mostly here as a ray, but with some squiggles to remind ourselves it's actually a wave. There's some wave stuff happening in there. It hits the eye, and then that sends a signal back through the brain, and the brain does something magical, and ideally, somewhere, an image appears, and the person perceives that there is a star there. So to understand the dynamics of everything that's going on here, we're going to narrow in first on this little interaction. Right when the light ray hits the eyeball, what happens there? We'll break this down into a couple of steps. And the first thing we need to think about is just like what happens in general when light hits transparent material. So your eye is slightly transparent. It's kind of like a liquid, but not exactly. Maybe more like a plastic on the outside. So when light hits any transparent material coming in from air, a number of different things can happen. You can have light reflect back off. which we certainly see, you know, when people's eyes kind of glitter a little bit, that's often the light reflecting back off the surface of their eyes. But it can also transmit, and that's what we want for vision, and we want light to come into the eyeball. Now, interestingly, when light does this, when it hits a transparent material, it doesn't just go straight through. It actually bends a little bit, it refracts, doesn't go straight. This is the source of when you look at something underwater, it's very distorted, right? It doesn't look normal to you. That happens because of refraction. So, why does the light ray bend? Well, it bends because light actually slows down when it goes into a material. Now, actually, going back here, I want to just show you this sort of in practice. We have this fancy little camera that we can use here. So I'm going to turn the lights down, but if you can't see the board very well, you can turn around and look at that little screen behind you as well. But we'll try to turn down the lights a little bit so it's easier to see. But you can see this phenomena of refraction here. We have the light coming in here through our little block here. And as I turn it, so I'm introducing some sort of angle now, sort of like what we're seeing up here. And we see that the light inside of the material doesn't go straight. It actually bends down. And the more I bend this, the more extreme that is. Now, something interesting is happening on the other side as well. We're not going to focus too much on what's happening there, although if you all have questions, have a chat about it. But this is basically the phenomena that happens anytime light enters into some kind of transparent material from air. And this bending happens because the light waves actually slow down as they enter the material. And I want to use an analogy here to make sense of this slowing down. So think about you're going to the beach and you have a cart in front of you that you're pushing. And as you are moving off the sidewalk into the sand, coming at a little bit of an angle, that first wheel goes off of the sidewalk and goes into the sand. What happens to that wheel? Yeah, it slows down. It doesn't move as fast. Now all of a sudden it's in sand, there's friction, it kind of sinks, it's just moving a little bit slower. But that other wheel on this side is still moving just as fast. And so that's going to cause the whole cart to turn. As that high wheel continues to move, it moves faster, this low wheel moves slower, and the whole cart is going to turn. That'll happen 2 times for the cart, once at the front wheels and once at the back, but the result is going to be that the whole thing turns. The same thing happens when you're talking about light. So when you're thinking about a light wave, and again, I'm talking about light as a wave now in this situation, in this, the little lines you're seeing, you can think of those as the peaks of the waves, and the empty space in between is the troughs. So you have your little wave kind of going like this. As you get a wave front that hits the material, this part starts to slow down. It's not moving as fast, and so it kind of bends away backward from the rest of the wave front, which just continues forward. And as that happens, you get more and more of the wave sort of bending backward because it's just not moving as fast anymore. And eventually you have the whole wave front into your material and it's now going in a slightly different direction. So same kind of idea, you get this bending of the light as it moves from air into some kind of transparent material like our eyes. So what does this tell us about what happens inside of our eyes? Well, unfortunately, everything I've talked about up to this point has just been about flat interfaces, and our eyes are not flat. They have 2 important pieces that happen way before your eye actually detects the light. This is all just about light gathering. There's the cornea here, it's that kind of like bumpy part of your eye, and then there is the lens. So to understand what really happens when light enters your eye, it's not enough to understand what happens when light hits a sort of flat interface. We need to understand what happens when it hits lenses. So how do we make sense of lenses then? Now lenses are a really interesting and rich area, but we can make a lot of sense of them just with what we've talked about so far. So a lens like the one in our eyes, we call these converging lenses. We're going to kind of break this down by individual light rays to make sense of what's going on. So there's one really easy light ray, and it goes right through the middle. And if we kind of model the middle of the lens as just sort of being a rectangle, well, it's just coming in straight. And you can imagine if your cart is coming in straight, it slows down, but it doesn't turn. There's no differential turning there. So it just kind of you know, does its own business, goes right through. Nothing happens to that ray. It's very boring. Now we can step it up. We go a little bit higher in our lens. And now I'm going to model this as sort of a trapezoid. So we have a little bit of angle to our sides here. And so now as the light ray hits that first side, we get that same slowing down, it bends down. As it leaves on the other side, we get the exact opposite thing happening. And because the angle is opposite, we get it actually bending even more down. So the net result of this is that a light ray that was previously sort of going up at this angle, as it moves through the lens, it actually gets completely turned around, going the other direction. We can do that one more time and it gets even more extreme up there at the top, where the angle between the two sides gets more extreme, we get more bending. Now, what's really important about thinking about this is actually what happens on the other side of the lens, because I'll notice that those light rays, they come together at this one little point. They started together over here, they came back together over here. That's where your retina is. That's where you want to put where evolution effectively has put the back of your eye. So we can also look at this on a nice little camera. Give me 1 second to set that up. This guy over here. Yeah. Okay. And so same sort of thing happening here. We have each of our light rays, in this case, coming in parallel, and they're hitting a nice little lens, which is sort of modeled to look like the converging lens that we have inside of our eye. And sure enough, they come together and they right at the back where the back of the eye would be right at the retina. That's where all of those light rays come back together to eventually form what we're going to find out in a minute is an image. So to take this one step farther, make a little bit more sense of what's happening. Here we have effectively, this would be our eye lens. This is our thing that we're trying to look at. For the lens aficionados in here, I've marked the focal point, if you're interested. I'm not going to talk too much about that, but for those of you who know a thing or two about lenses, we have our focal points on either side. There's 3 particular rays that are useful when you're doing these kinds of lens diagrams. And they move through the lens in very predictable ways, and they converge on the other side. And what this convergence is, all of these light rays started at the tip of our arrow, and they all ended up right here. And you can map this out for every point on the arrow. And what it will show is that you end up with a little image of the arrow on the other side of the lens. And it's upside down. That's interesting, because that is all that your eye is a single converging lens, which implies that you see the world upside down. But wait, you don't see the world upside down. Yes, you do. But your brain is really good, and it corrects for this. So your brain actually does get an upside down image of the world, and it knows to flip it right side up. Really interesting thing that you can do. There are glasses that you can create and put on that will flip the world upside down again. You can wear them, and for a couple of days, you're going to be real confused. You're going to fall down a lot, and then your brain will correct it. And your brain will flip the world again, and you will see the world right side up. Here's the kicker. Take the glasses off. It will take your brain another couple days to learn to reflip the world over. So your brain is a really powerful part of this system. And that's going to be like the message for the day. We'll come back to this a lot. So the last really important piece that we need to know about lenses before we can get into some of the more fun stuff is what's called lens power. Power is just how strong the lens is. So when you have really powerful lenses, they converge the rays really fast. And when you have less powerful lenses, they don't converge the rays quite as fast. They're not going to converge them, but it's a matter of how quickly. And this relates back to, if we remember, building our converging lens, the more of an angle we had, the more effect that we saw, more bending that we saw. Same thing goes here. As the lens gets thicker, you get more angle on more of the lens. As they're thinner, the angle is less. And so you just don't get quite as much bending. So this leads us to the first kind of application of this that we can to sort of concrete human vision, which is going to be eye problems. common eye problems that we see. I see many glasses out here in the audience. So many of you have concrete experience with these types of eye problems. The most common three that can be solved with something like eyeglasses, the first is myopia. Myopia is nearsightedness, which means that you can see things up close quite well, but you can't focus on things that are farther away. The opposite of myopia is hyperopia, and that is being able to see things far away, but not being able to see things up close. So this would be farsightedness. And the last one is presbyopia, and this is a lens that is too stiff. So in order to be able to adjust to being able to see up close and far away, that's your lens basically getting more powerful and less powerful. It's sort of, there's muscles that let it flex and change its shape to get more or less powerful as it needs to. Some people have lenses that are just too stiff and the muscles can't pull them enough. Now, interestingly, this is one that we will all probably suffer from. This is what happens as you get older. Your lens just gets too stiff, and this is why you often have glasses that have both a little window for like reading up close and a larger window for seeing far away, because the eye is having a problem with both levels. So with farsightedness, for example, hyperopia, the problem is that as the light comes in, the lens isn't strong enough. And so as it focuses, it actually focuses the rays, they would hit behind the retina instead of hitting right on the retina, which is what we want. So to fix this, we need a more powerful lens. We need to help augment what's happening. And to do that, well, we're just going to put another lens in front of it, another converging lens. And then that one is going to help a little bit by starting to converge the rays before they hit the eye. And then that will allow the rays to perfectly focus back on the back of the retina, just like they're supposed to. The lens that we use here is the same type of lens that is in your eye, and it's also the same type of lens that we use as a magnifying glass, which is why people who wear these glasses, especially when they're very powerful, often you'll see it's almost like their eyes are magnified. They look like little magnifying glasses when you see them from the other side. So that would be farsightedness. Nearsightedness is exactly the opposite. So in nearsightedness, the problem is that the lens is too strong. And so it actually focuses the rays too quickly, and they never hit the back. They don't hit the back of the retina where they're supposed to. And so once again, you're going to end up with a fuzzy image that isn't nice and crisp. To fix this, we actually have to talk about a lens that I haven't talked about yet. We've talked about converging lenses like the one in your eyeball. There's another type of lens that you can create, which is called a diverging lens. And it has exactly the opposite shape. So converging lenses have this shape. Diverging lenses have this shape. So you just basically flip it. And the result of that is instead of causing rays to come together, they cause rays to move apart. So to solve the problem when you have myopia, you put a diverging lens in front, and that allows the diverging lens actually pushes the rays a little bit farther apart, so that when this too strong eye lens gets them, it has to work harder, and then they focus once again perfectly right at the back of the eyeball, which is the goal. This has the opposite sort of visual effect. When you see people, you can tell what type of glasses somebody has by how it looks on their face. When you have hyperopia, you get that magnifying effect. When you have myopia, you actually get a slight sort of reducing effect. It makes their eyes look smaller. So those are some of the common problems that we have that can be fixed with eyeglasses. Now you might ask the question, what about contact lenses? Obviously, I can't tell who in here is wearing contact lenses. I'm betting there's a few. There we go. Got some hands up. Yeah, we definitely got some contact lenses in here. So the process is effectively the same. You want to correct that. You want to give the eye some help either to make it stronger or make it a little bit weaker. Now these shapes worked really well for eyeglasses. That worked fine. But what if these things need to sit on the curved surface of your eye? That sure doesn't look comfortable to me. Now, luckily, the shape is actually not, the shape is important, but many shapes can accomplish the same thing. And so you can actually create lenses that have very different looking shapes, but that accomplish the same goals. So these are roughly the shapes of the two types of contact lenses that you might achieve here. And these do the same thing. They have the same impact on either spreading or converging of the rays to allow these to sit comfortably on the surface of your eye. So for anybody who has contact lenses, if you looked at them closely, this is what they would look like. Okay. I'm going to switch gears on us a little bit, unless anybody has any questions so far. Yes, please.
I hope there was the other one, you always have these parallel rays coming in.
Mhm.
Relates to the business, the way the object is.
Yeah, this is a really good question. So the question was, why do I always show these parallel rays? And this is actually a really good point. The parallel rays are purely for convenience of the figure. If we go back and look at, for example, this, we will get the same types of effects even when the rays are not coming in parallel. It's a little harder to draw, which is the only reason I didn't draw it that way. But to your point about distance, that's exactly right. For something like this to come in with parallel rays, it would need to be very far away from me. In effect, it actually happens pretty quickly. It's actually surprising how fast it does happen, but things need to be about 100 meters away from you before you start getting pretty close to parallel rays coming in. And it's not perfect, but it's pretty close. Did that answer your question? Good question. Others? Okay, so we're gonna take a little bit of a zig here because light is more than just what we see. In fact, light is in a broader camp of what I'll call broadly electromagnetic radiation. How many folks have heard that phrase before? Electromagnetic radiation. Yeah, okay, so most folks have heard that before. Now, while most people have heard about electromagnetic radiation, it isn't always that we connect that word with light. But as far as a physicist is concerned, any EM radiation is light. Now, that EM radiation spans all the way from sort of radio waves down here to what your microwave does, to UV rays that give you a sunburn, all the way up through X-rays and gamma rays, which can now start to become damaging. The part of this whole giant spectrum that we see is quite small. It's just this little tiny strip in the middle that I've blown up here. And this is what we will often call the visible spectrum. When people colloquially say light, this is usually what they're talking about. Now, the striking thing about this is always it's a rainbow, which leads me to the next question of what is color? How does that manifest and how do we perceive color? So color, the thing that our eyes detect when it's detecting color is wavelength. Technically, it's frequency, although that's a subtlety. Usually we can talk about those two things somewhat interchangeably, wavelength and frequency. I'll talk about wavelength today, although for the sticklers among us, technically it's frequency that your eyes detect. So red is on one end of the spectrum, and it has a very long wavelength. And so by that, I mean, if I'm sort of thinking about how many cycles does it make in a certain distance, it doesn't make very many. You get only a few cycles in a set distance. As opposed to, for example, violet down here, it's gonna make a bunch of cycles in that same distance. It's a much shorter wavelength. Our eyes can detect these differences in wavelength, and that's how we figure out what color something is. But to talk about exactly how our eyes do this, we need to go back to thinking about the structure of the eye. The only thing we've talked about so far is kind of the cornea and the lens. This is the light gathering end of the eye. Now we're going to switch to talking about the light detecting end of the eye. So the light detecting end is the retina and the sort of optic nerve coming across it. So your retina has a shocking 100 million nerve endings in it. It's probably one of the most sensitive parts of your body. And those nerve endings are typically either rods or cones, and we'll talk more about those in just a second. They're mostly centered right on the back of your eye, right behind the eye lens, but not all. They're all along the back of your eye. And the optic nerve also has about 1 million transmission lines to the rest of your brain. Again, just a highly sensitive, nerve dense area of your brain. Rods, which are aptly named, as you can see here, they're these little rod-shaped things. Those are what handle vision in low light. They're denser on the periphery, and that's why you can sometimes see dense things or dim things better from the corners of your eye. I don't know if you've ever experienced that. Cones handle color and detail. They're denser towards the center. There are 3 different types of cones. Each one responds differently based on what frequency or what wavelength of light is hitting it. So short wavelength, down here at the more like 400, 450 nanometer, we have one cone that responds strongly to that light, but basically won't respond at all when hit by light up here at the 700 nanometer. And vice versa, we have a long wavelength cone that will respond strongly when hit by these 600, 700 nanometer light waves, but won't respond at all to this 400. So we name these based on the wavelength that they respond the best to. So they're red, green, and blue. So we have a blue cone, a green cone, and a red cone. These cones, these cells, can do only one thing. They can either say, yes, there is light, or no, there is not light. They do not measure intensity, so they can't tell you how bright the light is. They can only tell you whether or not the light is there. And they also can't tell you something like or rather brightness or intensity is actually your brain interpreting how many cells are firing. But this introduces an interesting question, because if your eyes can't actually detect what color, they only just say, yes, there's light, or no, there's not light. That's an interesting question, because like, say, if we look right here, I could stimulate the red cone by shining red light on it down here, or by shining orange light on it. So how does my brain know whether or not it's red light or it's orange light? All the cell says is there's light. How is it that the brain puts together what the color actually is? So to make sense of that, we're actually going to switch to a little sim here that'll let us play with this. So if I pull up my red light here, then my eyes see the red light and they see red. Great. But then what happens if I throw a little green in there? All right, I'm not getting something closer to yellow, maybe? So what your brain is doing when it's stimulated, it's looking at ratios of how much of each cone is being stimulated. And so if I wanted to figure out how to make orange, I would play a little bit with, maybe I have a lot of red light in there, maybe a little less stimulation on the green. So my brain says, oh, my red cone is really going. My green cone's going like a little bit. And it's like, oh, well, that's orange. A lot of red and a little green. And similarly, we could do something with, let's say, a lot of green and a lot of blue. What's that going to give me? That's a tricky one, by the way. Teal, cyan, something like that. Now, here's a hard one for you. What happens if I give it a lot of blue and a lot of red? Purple. Purple's a really good guess. It's not quite purple. It's a color called magenta. And it's fake. There is no magenta in the rainbow. There's purple in the rainbow. There's violet in the rainbow. But magenta does not exist in the rainbow. And that is because there is nothing, usually when you have if you have red and green, you get yellow. Yellow's right in between red and green on the rainbow. What's between red and blue? They're like wrapping back around. And so your brain doesn't really know what to do with that. There's no color associated with that. So it makes one up. So it makes up magenta. It's not a real color. You can't have a magenta light except by creating a light that shines both blue and red. That's the only way you create that color. So again, getting back to the idea that your brain plays a huge role in this in terms of the interpretation part. And sometimes it just makes stuff up. So here's another place where we can talk about what happens when color perception goes wrong. Talked about what happens when the lens goes wrong. So Color vision problems can happen in a lot of different ways. You can have that the cone is kind of shifted in its sensitivity. You can be missing one of the cones. There's also things that can happen in your brain where the channel wiring is wrong, where like the green should go here and the yellow should go here and we've crossed them. All of these things can happen. And usually this results in some kind of inability to see particular colors or an inability to distinguish between particular colors. So we can do a quick test for ourselves here. I won't make you raise your hands, but I'll ask you the question of what is the sum of the two numbers here. And if you're in the numbers, what numbers camp, I maybe suggest that you go see an eye doctor and find out if you have some mild amount of color blindness. Not to keep you waiting, the answer is 23. There's a 15 in the first circle and an 8 in the second. Different types of color blindness that you will see. This first one, protonopes are missing the red cone and deuteranopes are missing the green cone. Protonomalous and deuteranomalous, those are where your red cone is either shifted down to the green or your green cone is shifted up to the red. And so basically there's no difference in the response between these two, which means your brain can't tell when you're just stimulating one or you're stimulating one more than the other. The most common of this is red-green color blindness. That's the deuteranomalous. That's where the green cone is shifted too high. It's one of the most common forms of color blindness. If you're ever writing lectures or presentations, do not put red and green as the only defining colors between your graphs and things like that, because colorblind people will not be able to tell the difference. It's not that they can't see, these people can't see red and green, they can see both colors, but they can't tell the difference. Their brain cannot distinguish one from the other. And so, for example, a field of red flowers with green stalks would look very much like a field of whatever color they perceive that to be, but they wouldn't be able to tell the difference. So it would just all look the same. It would maybe all look green or all look red or all look like something else their brain interpreted it as. The others have similar types of things that will allow them to see various different distinctions. Can this be fixed? That's another interesting question. So can color blindness be fixed? The answer is sometimes, kinda. And the way that we do this is something called achronia glasses. So what these glasses do, and I'll sort of walk you through what this figure is saying. Here we have our red cone stimulation. We have our green cone sort of response stimulation. The glasses overlay a filter. And by doing this, they block out all light in this area. So this whole section of light where there's the most overlap and the most similarity between the stimulation of the red and green cones, they just block that light out completely. That light never reaches the person's eyes. They also block out the tail ends where, again, the stimulation is similar. So now, if light hits them over here, now that's mostly red light, they're getting a much stronger response in their red cone and a smaller response in their green. Same thing over here. This is green light, much smaller response in red, larger response in green. So what this does is it augments the difference in stimulation between the two different cones. What was normally a small difference in stimulation is now a bigger difference in stimulation. And it allows the brain to learn the difference between red and green light. Sometimes this takes time, and unfortunately, it doesn't work for everyone. But there are a number of people in the world. If you want to give yourself a nice little tear jerk, you can go look up the videos where people like buy their family members colorblind videos, and it'll just destroy you. It's like super heartwarming. So sometimes these things can be fixed or at least augmented. Oh, yes, please. Why? Was that your question? Yeah, it's just because down there, the stimulation again becomes similar. And so it's just easier to notch that out as well to help just augment the signal difference. It's also, I mean, fundamentally, I don't think you would have to do this. And I think the wideness of this could also be impacted by the difference in like how much are they overlapping. These glasses can be custom made to have different amounts of filter to help somebody with different exact overlaps augment the chances that the glasses will work for them. So it's not just one type of filter. You can have many different types of filters for the different degrees of overlap that different people have. Yeah, good question. Okay, so we're gonna move on to just some like fun applications of these ideas and interesting things that happen. So humans evolutionarily are daytime predators. We need detailed and precise vision, especially during the daytime. This means that the cones are concentrated right at the back of our eyes, right on that fovea. That gives us the most detail. The rods, which are more sensitive, are on the periphery. And there is a blind spot. I'm sure many of you have heard of a blind spot. So that's where the optic nerve attaches. There are no rods and no cones at that point, which means that your eye does not detect any light at that point on your eye. Side note, I would like you all to put your eye patches on right now, please. I'll do it too. So we're not, nobody looks, no, it doesn't matter which eye, just have to pick one. Either your least or your most favorite eye, depending on which you want. Now, it is relatively important that you let these kind of just like close your eye. That's the easiest way to do this. Like, don't try to keep your eye open underneath it. Just kind of close your eye. You want to kind of completely block off as much light as possible. So it is relatively important that you do not take these off and that you kind of let them sit. So we're all going to look a little bit funny here for a bit. I'm going to be like missing anything that happens on this side of the room. So shout if you need me, but okay, but we're going to move on while we sit with these on. Okay, so as I mentioned, the blind spot is the point in your eye where you have no rods and no cones. And that means there's no light hitting that point. So the question is, why don't we see our blind spot? You have two of them. There are 2 points in your eye where you are getting absolutely no light from it. So why don't we see this? So the answer, once again, as the answer to most of these questions is our brain. And our brain is very good at this. It fills in the gaps. And so if you don't believe me, we're going to try this. We're going to find your blind spot. So hopefully all of you have this nice little piece of paper, these little strips that I've created for you. So we're going to do an experiment. So the way that this works is with the eye that does not have the patch on it. Normally you would just close an eye, but we have a patch, so we don't have to worry about it. You're going to put the O right in front of your eye. It's fairly important that it stays directly in front of your eye. Don't start going out to the side or something like that. Right in front of your eye with the X out to the side. And you're going to kind of put it up close. You're going to focus only on the O. Don't take your eye off that O. Let yourself see the X, but only in your peripheral vision. And then you're slowly going to move the paper away from you, focusing on that X until the X, or focusing on the O until the X vanishes. It'll just go away like it's not even there on the paper. Everybody find it? Anybody still not able to find it? So you want to make sure, once again, don't let yourself go out to the side. Make sure you're right in front of you. And make sure you're kind of going slow because it happens quick. And you'll just find a point, it's right about there for me, where the X is just like gone. You can like look at it and it'll reappear. But as soon as you focus back on the O, the X will vanish. Did we get it? Everybody get it? Awesome. So that is your blind spot. That is the point in which your optic nerve would show up in your field of vision. And sure enough, your brain is really good at this. Your brain, the X enters that area and your brain says, oh, I see white all around this. So I'm just going to put white in the middle. It just fills in the gaps. And this happens all of the time, and your brain is really, really good at it, like 90% of the time. Another interesting thing about our eyes is that, as you might expect, for order for any cells to work, there has to be blood vessels. And so there's a sort of a branching pattern of blood vessels behind your eyes. And you might interestingly ask whether, by the way, this is what causes red eye when you take photos, is light reflecting off of those red blood vessels on the back. So why don't we see these blood vessels? Why are they not just there in our vision all of the time? We do. They are there in our vision all of the time. And once again, I'm going to prove it. So what we're going to do now, I'm going to need you to take out your phones. Don't do any of this until I tell you to, though. So I'm going to dim the lights. You're actually going to turn on the flashlight on your phone. And once again, with the eye that is open, what you're going to do is you're going to stick that light, and I'm going to block it for myself for a second, as close as you can, kind of right underneath your eye. Oops, wrong way. See, I did it wrong. You want the light as close to you as possible. Right underneath your eye. I'm going to dim things down, and you're going to just move that light just a tiny, tiny bit. And you're going to see what you see. I'm going to turn the lights off. Don't let it go for too terribly long, because that is going to be bright. You will find it does blind you a tiny bit. So right as close to underneath your eye as you can get it, and just move it back and forth. Just really slowly move it back and forth. And just focus forward on like the board. Can we all see that? Do you see that branching pattern up here? That is the structure of the blood vessels on the back of your eye. It is there all of the time. You see that constantly. But your brain, once again, filters it out. It sort of has recognized that it is irrelevant and it doesn't let you see it anymore. So all sorts of really interesting things happen with your eyes. So I want to talk next about night vision, which hopefully you all know now why they have the eye patch on. So night vision, if we look at the distribution of rods and cones within our eye, the rods are very dense out towards the ear and the nose. So if you're sort of scanning across the back of your eye out here and out in here, you have a high density of rods, very low density of cones. The cones, on the other hand, are very dense right in the middle, just right in the center of the fovea. Now, our eyes can adapt to darker environments. Certainly you all have experienced this. Now, for about the first 10 minutes, the lights and cones get more sensitive, trying to compensate for the lack of light. At which point your brain kind of gives up and it just switches to just the cones, and it makes the cones more sensitive to try to gain more light. And so this, as a sort of a function of time, this looks a little bit like this. We start out, the light is gone, and the sensitivity of the cones this is actually sensitivity going up, so this is the threshold for how bright the light needs to be to make the cone fire. So that threshold is going down, the cone is getting more sensitive. And then at some point, it stops trying to do that. Your brain stops trying to do that, and it goes down to the rods. Those get more sensitive. That will sort of plateau out at some point, but they will get more and more sensitive. Now, I think we're at about 15 minutes here, I feel like. I think it's been about 15 minutes and put these on. So we're just going to go ahead and give this a shot. So don't take it off yet. I'm going to turn the lights off. And what you're going to do is you're going to take the eye patch off, and you're going to just switch back and forth between which eye is open. And I want you to notice the difference in the room in terms of what you can see. So don't take it off until I've gotten like everything covered. And that's going to include this little light here, which I'm going to cover up. Okay. All right, we're going to turn all the lights off. Okay, and now I recommend looking forward as much as possible because those lights are there a little bit. But okay, so take your eye patch off and just switch back and forth between the two eyes. And you can see how powerfully different the vision is. Now that was probably almost more like 12 minutes. So we were only just barely to the point where we'd really turned off the cones and started focusing on the rods. You let that go for another 10 or 15 minutes, it is stunning how much more you can see. Now it's really, you don't normally notice this. I guarantee you've experienced this before. But you don't normally notice it because normally it's happening to both of your eyes at the same time, as opposed to only one eye. Luckily, it also goes away very fast. So we've just ruined that 15 minutes of work that we did, and now your eyes will no longer do that. Cool. Yes, please. It is the brain that is adjusting this. It is, I mean, fundamentally how the brain is adjusting, I suspect that probably is some kind of chemistry, and I don't know the answer to that. But this is your brain that's deciding what should be on at what times, and it ramps up sensitivity. It does this also, we probably won't get to this today because we won't have enough time, but it does this also in just the very way that we see, in terms of how your nerves respond to stimulation. It's why humans are very good at being able to see changes in color and changes in intensity, rather than just like necessarily total brightness. Any other questions? Yes, please.
Train the brain, the order. Turn on the game more for the night vision.
I believe that you can, but it is something that gets wiped out as soon as you see light again. So I don't know that it's possible to train your brain to be more efficient at doing it, but I don't know that for sure.
Country dwellers and city dwellers.
Yeah, interesting question. Yeah, I don't know. I would assume that they still both have the same sort of minimum that they can reach. It's just that city dwellers won't reach it very often. Whereas, folks who get to go out into the night sky or, have darker environments will be able to reach that faster. But that's an interesting question. I don't know the answer to that. Do you?
I was in sailors will sometimes have an eye patch for
Right.
exactly this.
Yes, this is exactly why I wonder if that's why pirates got the eye patch. Yes, okay, so I actually, I won't show it to you. I have actually have a slide about this. So why do we use red light when we don't want to destroy night vision? That actually comes down 100% to the sensitivity of the cones, or sorry, the rods. So the rods are highly sensitive to light, but it tails off, it's kind of light in the middle of the visual spectrum, and it tails off hard at both edges. It basically cuts off red light in its almost an entirety. So your rods are actually very insensitive to red light. Highly sensitive to almost every other kind, but not red. And so you can shine red light on your, so when you've turned off your cones, it's already dark, you're already in your night vision space, it's your rods that are seeing for you, and they don't see red light. They're really bad at seeing red light. So you can shine red light, and now all of a sudden your cones are like, ooh, I can see that. And so they can perceive in the red light, but that doesn't ruin the sensitivity of the rods. So when you turn the light back off, you still have your rods at full sensitivity, your cones just turn back off. But really good question. Others? Okay, in the last few minutes, I'm just going to chat a little bit about animals. And how animals see a little differently than us. This is impacted by a lot of things. Again, we've talked about your visual system is both eyes and brain. It's also impacted by how everything is structured. So this can include things like how much of the spectrum do you see? So which photoreceptors do you have? What is the structure of the eye itself? And where is it on your head? All of this impacts what you perceive. So there are animals that see parts of the spectrum we cannot. So as I sort of mentioned before, the electromagnetic spectrum is much more than just the tiny visible spectrum that we see. So for example, birds, bees, interestingly, reindeer, I don't know why reindeer are on this list. Fish, rodents, they all can see, many of them can see in the UV, which is what burns our skin. They can perceive it. Infrared, snakes, some other fish, blood-sucking insects, some amphibians like frogs, can see in infrared light. And this is often, but not always, accomplished by having an extra photoreceptor in the eye. So for example, birds see in the ultraviolet. They have an extra cone. So they have the normal 3 cones that we have. They have a 4th cone that is up in the UV. This actually makes their perception of color much more brilliant than ours. So for example, here's what a human might see for a bird. And it's pretty. There's got some iridescence happening here on the shoulder. There's some color there. Obviously, this is false color because we can't actually perceive this, but this might be more like what a bird would see. All of this incandescence here is reflecting the UV very strongly. And so the bird is perceiving a lot more color and color variation than we are capable of. This also does things like help them find eggs. So eggs might look kind of drab and dull to us, but they also reflect UV light, and so they tend to be much more brilliant to a bird's view. Bees are another one. Now, interestingly, bees, unlike birds, don't have the extra cone. They have the same 3 cones that we do, except they've kind of combined the red and green cone into just one. And then they have what they would have had down here is actually up here in the ultraviolet. And they do this for the exact same reason that the birds do, which is they want to be able to see things better. And what do they want to be able to see? Flowers. They want to be able to see flowers. And flowers want them to be able to see them. So there's a coevolution happening there where flowers, we might look at a dandelion and say, oh, that's just a pretty yellow dandelion. Whereas a bird, the flower itself actually has a center that reflects the UV very strongly. And so to a bee, it sees a bullseye. The flower is telling it, come here. And the bee's like, yes, I would love to. Snakes see in the infrared. And I put see in quotations here because snakes do have an extra photoreceptor, but it is not in their eyes. It is in two little pits on the sides of their heads. So this is a totally different organ, but it is still feeding into their vision in the sense that the vision happens in the brain, right? That the picture that gets formed happens in the brain, it doesn't happen in the eye. So for a snake, they put together both what they're seeing with their eyes, with what they're seeing with their infrared detectors, and we end up with cases where things that are giving off infrared radiation, which is all of us and all warm-blooded creatures, snakes are capable of seeing us basically glow. We're like light bulbs to snakes. They actually give off a lot of radiation, yes.
They have like lenses in front of those infrared detectors, like do they put together a full picture, or is it just kind of two old down?
I don't actually know the answer to that. It's a really good question. I might actually imagine it's not so much more like a lens as it is almost like if you think about like a telescope. So it's a little bit more almost like echolocation for light, but not the typical lens type of thing. So yes, I suspect you're absolutely correct. They probably don't see with a lot of detail with their photoreceptors, but when you combine that with their vision, I suspect their brain can make sense of it. That's a really good question. We'll end with just a quick conversation about dogs and cats because why not? I mean, can't really talk about this without talking about the two animals we encounter the most. So dogs only have 2 cones. They do not have 3. They'll have vision very similar to someone who has red-green color blindness. They have fewer cones as well, so they just also don't see color quite as well as we do. So we might see something like this where there's sort of brilliant color. The dog, that's going to be far more drab. They're not really going to be able to see that distinction. This is also, by the way, if you throw a red ball in green grass, your dog's going to have a hard time finding it. But they also, like snakes, have that extra thing that they're dealing with. They have their nose. So they also kind of see in some sense with their sense of smell. Again, not exactly the same. They're not forming images the way that your eyes do, but that feeds into their image and perception of the world in interesting ways. Also, side note, they're somewhat nearsighted. So your dog can see at 20 feet what you can see at 75. So that, you get all of those cute videos where a dog's owner comes home and they look very different and the dog gets all like standoffish until they can smell them. It's literally because they can't recognize them. They just don't really have that good of vision. Most of what they take in is mostly actually smell, not vision. But they have many more rods than humans do, which means they're much more sensitive to light and they're much more sensitive to movement. So when things move in their vision, they catch it really, really fast, much better than we do. Cats are similar with a few small changes. They also only have 2 cones. There's some evidence to suggest they see a bit more green or they distinguish a bit more green than dogs do, but it's pretty slight. Again, they have many more rods than we do, so they're much more sensitive to movement, much less sensitive to detail. So this might be a comparison. A human might see sort of this top fisheye image, and a cat might see something more like this. It's just, there's not as much color, the details are fuzzy, the background is real fuzzy. They just don't, not as much happening. But again, part of what they're sacrificing there is they will be perceiving the movement much more sharply and clearly than we are. So it's that trade-off for them. In terms of night vision, cats and dogs, part of the reason their eyes work the way they do is because they are nocturnal creatures. They see much better in the dark than humans do. So you might, again, get a human seeing a plaza that looks something like this and a dog seeing something like this. I really like this picture because this to me is what the night vision thing does when I do the night vision test that we just did. This is kind of what it feels like to me. It feels like one eye sees this and one eye sees this. And again, you notice the lack of color down here, a little bit less detail, but much brighter. All right, well, that puts us just about at 3:30. So I'm going to go ahead and stop us there. But I don't know if we have time for other questions or anything like that. But thank you all very much for coming. I've had a great time chatting with you all today. Sorry. Didn't know what we want to talk about. Yes, please.
crayon. Trains them to identify new colors other than the ones that the brain actually can identify, like labeling magenta. And if all the collections that are using crayon have not trained their brains, then we have a different problem.
Yeah, I think you're right. And so I'll actually, I will mention a historical oddity in response to this, which is that there's a lot of evidence to suggest that for a long time, the color blue didn't exist in some sense. Like nobody ever talked about blue. When you asked people to describe the color of the sky, they would say violet. There wasn't a word for it. The word blue did not exist. And therefore, people's perception of the color was effectively muted. People wouldn't be able to distinguish different shades of blue very well. It was all just blue.
Yes. Interest in linguistics and who has read about studies of this type, that's not strictly correct.
Oh, okay.
It is that this has been tested in cultures that don't have some of these colors, words for colors that we do. It's like there's a box of yarn skeins and colors, and you give them to these people who don't have words for blue. They can match the different shades of blue ones together.
Okay, so it's not necessarily they don't perceive them, they just don't talk about them.
There's kind of, it's interesting, there's a progression of color words that appear in language. Starts almost universally with black, white, and red. Then eventually the next words that get added are green and blue in some order, and then it moves on to like yellow and brown.
Right.
And a new word is always derived from an object or something that exists that is that color. So when it becomes relevant for a culture to meet this word,
Right. Then it invents it.
then it's, well, it's colored like this.
Right. Right. Yeah. So I think relative to your question, yes. I mean, I think that like the fact that we give people crayons that have colored names on them and we can explore them in certain ways absolutely it impacts how we think about and talk about those colors. Now, maybe it doesn't fundamentally affect how we perceive them, but it certainly, I think, affects how we interact with them. Yeah. Mm-hmm. Oh, that's a fascinating question. Way outside my expertise. Yeah, no, I do not know. It's a really great question. I mean, I think the development, not only, I mean, again, the brain is such an integral part of perception. It's obvious as the brain develops that is going to impact perception in really powerful ways. So I think that connection's got to be really interesting, but I don't know. Yes. So when the sun is really, so like it's like when it's right up in the sky or when it's like down on the horizon? Yeah, I'm gonna guess that's actually more of just like an intensity issue that like there's so much light coming into your eye, you're effectively overwhelming your photoreceptive cells, and they're just like firing like crazy, and your brain can't turn them down fast enough. So that's the interesting thing. The reason we had to have those eye patches on for as long as we did is that your iris can control some degree of the light coming into your eye quite quickly. Iris responses are quite fast. The brain turning the sensitivity knob down, that process does not happen quickly and cannot happen quickly. So my guess is in that scenario, it's basically just there's so much light that your eye is just overwhelmed and it just wants you to close your eyes because it's just like, too much. Good question. Others. Paul?
John Rogers was telling me a story, reading an article about a person who had not been able to see since childhood because of some problem with the optic nerve, and there was a therapy using stem cells that managed to regrow that portion of the optic nerve, and the person could see for the first time in 40 years. And they could see the colors and things like that, but they were never able to learn how to perceive, say, a face. So that portion of the programming in the brain was not able, at least in a period of a year or so, able to organize itself at that level.
Yeah.
So vision was there, but the processing had never developed.
Yeah, facial recognition, again, this getting back into the role of the brain, that is something that is learned very, very young. And it's why we're particularly good at it. It's also why we are particularly good at recognizing the types of people we spend the most time around, which is, for example, Caucasian people are best like being able to distinguish Caucasian people. The same goes for Eastern Asian folks, who will often say that all white people look the same, which is in part because we kind of do to them. They did not learn the patterning that we learned, and the same goes the other way around. So it's even not even just being able to recognize faces, but we learn very deeply specific features that our brain learns to pay attention to, and it happens very young. Awesome.
Thank you for coming. The next talk is on December 7th.
Thanks, everyone.
If you wanna,
Oh yeah, please do bring the eye patches back. You can keep the slips. If you want.
get there.
Do you teach here at the university?
Lots of different things. Some version of physics. I have taught many of the upper division courses.